This video is going to talk about parametric equations. Parametric equations are where you create something called a parametric curve. Parametric equations are actually where you have a third of variable that's involved. So as an example, which would create a parametric curve, is that you have x, which is a function of some variable, we'll call it t in this case. And then you have y, which is also some function, a different function of t. And so x and y is actually f of t and g of t. That's actually the point. And so we can actually graph this and look at what this looks like. I don't have the actual equations here, but I can give you some idea of what a parametric function would look like, parametric equation would look like. So parametric equation would look like something like we've got an axis, and then maybe we have some function that's going along some curve. This doesn't have to be a function, so it can actually come back on itself, but you have some object that's traveling along this curve. And the direction of the curve is very important. So you would put down the direction. A lot of times we have a starting point and an ending point. And so you restrict your time down to, or your, what we call the parameter, down to a starting and ending value. We call this a curve, it's a parametric curve. And then we can actually look at parametric equations. So parametric equations are what we basically just said. X is a function of some variable t. Y is a different function of some variable t. We use these a lot in physics. Physics actually uses these all over the place, where you might actually have a time here as your one variable, and you're going to see where you are in space based on a certain time. Again, t is what we call the parameter. It doesn't always represent time, but I'm from a physics point of view, so to me that does work better. The t will determine your x and y, and then your curve is your parametric curve. A lot of times, like I said, t is restricted between some values. So a might be less than or equal to t is less than or equal to b. You restrict yourself down. So let's go ahead and take an example. Here's a parametric equation. X is equal to t squared. Y is equal to 6 minus 3t squared. And what we're going to do is we're going to go ahead and find some x and y values for certain t's and see what we get. And then from there, we can graph this. So I'm going to create a table of values. But instead of the table of values just being x and y, it's going to be, I usually like to start with t, just because it's just easier for me to start with a t. And then we're going to find the x and the y. A lot of times we write them as ordered triplets x, y, t. So maybe I'll pick t equal to 0. If I put 0 in for what x is equal to, then I get 0 squared. So x is equal to 0. And y would equal to 6 minus 3 times 0, which is 6. I could then pick another t. Let's pick t equal to 1. Then I would get 1 squared, which is 1, and 6 minus 3t, which is 3. And then maybe I'll pick x equal to, t equal to 2. Then 2 squared is 4. Put 4 in for t, I get 6 minus 3 times 4. 3 times 4 is 12, so 6 minus 6 is negative, 6 minus 12, sorry, is negative 6. Let's just go to 3. 3 squared is 9. And then we had 6 minus 3 times t. Oh, wait, I have the wrong answer, sorry. So we put 2 in. So we have 6 minus 3 times 2. 3 times 2 is 6, so 6 minus 6 is 0. Sorry about that. Then we put 3 in, and we're going to have 6 minus 3 times 3 times 3 times 3 is 9, and 6 minus 9 is, of course, negative 3. And then we'll put 4 in. 4 squared is 16. 6 minus 3 times 4 is 6 minus 12, which is negative 6. So now we kind of have our values. We can now draw up an x and y plane. And I think I need to make my plane a little bit bigger. So I'll move it around a little bit. So I notice my x's go from 0 up until 16. So I don't need to go to negative x's. So maybe I'll go 2, 4, 6, 8, 10, 12, 14, 16, and just for yaks, I'll go to 18. Now, make sure I get 0 in here, so I'll put my axis here, my y-axis. My y's go from negative 6 to 6. So negative 6, negative 5, negative 4, negative 3, negative 2. Of course, you can do this. So my first point is when t is 0, x was 0, and y was 6. So there's a dot. I'll make it a different color just so you can see it easier. Then my next t has a x is 1 and y is 3. Then my next one has an x is 4 and y is 0. Then x is 9 and y is negative 3. And then x is 16 and y is negative 6. And if I connect these dots up, it looks something like this. And the more important thing is, first off, it just started here and ended here because t was restricted between 0 and 4. So we're not going to draw arrows on the end of that. But I am going to draw an arrow that says what direction my time was increasing. So I noticed that this was t equal to 0, and this is t equal to 4. So my time is increasing, or my t is increasing as I go that way. It looks a little bit like a parabola. We can actually prove it is if we actually were to take this equation and what we call eliminate the parameter, which means you just kind of get rid of that t. So you might go ahead and take this, of these two equations, it looks like it's easier to take the second equation and solve for t. So that would give you y minus 6. Actually, no, we're going to do 6 minus y. So I don't have too many negatives going on. So we're going to have 6 minus y over 3, and that's what t is equal to. And then we can put that into the other equation. So x is equal to t squared. So it's 6 minus y over 3 squared. So you can see it is a parabola, a sideways parabola, but it is a parabola. And that's what we call eliminating the parameter. Let's just do one more example of this. We'll take this example here. So we're going to go ahead and find the x and y and t values. In this case, it's not t, it's theta. So here x equals 4 cosine theta, y equals 5 sine theta. Theta is between negative pi halves and pi halves. So again, I'm going to make up a little chart of theta values, x values, and y values. And my theta values, I'm going to start, because my theta is restricted between negative pi halves and pi halves, I'm going to go ahead and start with negative pi halves. So if I put negative pi halves in there, 4 times the cosine of pi halves, negative pi halves is 4 times 0, which is 0. And then 5 times the sine of negative pi halves. On the sine of negative pi halves is negative 1, so we get negative 5. Then we'll go to maybe 0. So if I put 0 in, I get 4 times the cosine of 0, which is of course 1. So 4 times 1 is 4. 5 times the sine is 0, which of course is 0, because the sine of 0 is 0. Then maybe I'll come up here to pi halves. Now, I probably should have picked some more, Let's see if I can't get enough of this. I could have picked negative pi fourths and pi fourths and so forth, but we'll go with this. So if I put pi halves in there, I get 4 times the cosine of pi halves, which is 0. And 5 times the sine of pi halves, which is 5. And again, I'm going to go ahead and draw this. My y's go between negative 5 and 5. My x's go from 0 to 4 to 0. And then I've got when theta is 0, I've got this point 0, negative 5. When t is 0, I get the point 4, 0. And when t is pi halves, I get 0, 5. You can't really see this because I don't have enough points in here, but I bet this does something like this. Again, when t is a smaller number, negative pi halves, or theta in this case, I'm starting at 0, negative 5, so this is my starting point, and I'm going along the curve this way. So I usually put an arrow showing what direction my parameter is increasing. If you want to, you can actually also eliminate the parameter with this one. The way we would do that in this case is remember that sine squared plus cosine squared equals 1. So cosine, sorry, I won't do square yet. Cosine of theta is going to be x over 4, and the sine of theta is going to be y over 5. And then I remember that cosine squared theta plus sine squared theta equals 1. So cosine squared would be x over 4 squared. Sine squared would be y over 5 squared equals 1. So you get x squared over 16 plus y squared over 25 equals 1. And this is an ellipse. And so you kind of see we have half of an ellipse going here. If this had gone longer, we would have come up over here with the other half of the ellipse.